So welcome everybody to this session on Tidyverse. This is actually the third part of a series on Tidyverse. Turns out to be a fairly deep topic, but it's a by an example. And I was just going to say, if you go YouTube and SharkNet, you go to our channel here, and you do the question mark. I mean the magnifying glass lets you search, and you search for Tidyverse. You will see the part 1 and part 2, and of course, after the talk and when Sergey gets a moment, we'll be posting part 3 up there as well. So where were we last time? Well, we were in the middle of digitizing this example. So this sort of talk came out of I've done a few on ggplot and stuff like that. A few courses, and people were always asking, well, is there something on the wider Tidyverse? So decided to do an example as a motivation, and a lot of Tidyverse is about wrangling your data. So your data is in some sort of messy format that is got issues with it, and you want tools to easily bring that into a format that you can actually compute the sort of stuff you're interested in. So this is an example of some extremely messy data. This is the Canadian Flight Supplement, which is documentation provided by Nav Canada of all the places you can land at across Canada. So all the way from the big airports to the little farmer strips. And they just provide it in this PDF format, but it'd be nice to be able to use some of this data outside of this. So there's a program that I ran against this that converts a PDF into a text file. And it was not able to handle this well at all because it's a highly structured document. Where it does a great job if it's just paragraphs and stuff like that, but there's lots of implicit structure in this documentation. So then I thought, well, I'll practice my Tidyverse by bringing out that structure. So what I started with here, I'm just in my Emacs session here. If we load this up, there is, let me see. Oops, no, that's not the right one. Yes. So this was the output of this converter program. And basically, it gave me page numbers and estimates of what it thought were paragraph and block numbers and bounding boxes for each bit of text on the screen. So each word, basically. So CFS, digital editions, caution, information, and so on. So that's the input to this data. Basically, we've got the words and we got their bounding boxes and their page numbers that they are on. And from that, we want to manipulate this data using the Tidyverse functionality to bring this back into a format that's useful. So I think it's a bit of an extreme example of it, but a good example for Tidyverse. So that's a good coverage. So where had we gotten to? Well, we'd done a lot of work. We broke this out into pages, and we had the headings, and we had picked up the particulars of what airport, for example, this one's Ajax Pickering General Hospital, a helipad, and we'd extracted the identifier and stuff like that. And we were just starting to work on this sort of information here. And specifically, we were working on these labels here. So let's draw a line here. A lot of the high level sort of stuff we did by location. So we split our data down. Oops, let me get the proper pen here. We split our data down a line here on the left-hand side. And then we were looking at whether it was left aligned or right aligned, sort of determine whether it was a level 1 label or a level 2 label. And then for all the level 2 labels, we brought down the level 1 heading. So for example, flight plan has a bit of data with it. And then this is flight plan under the FIC, Flight Information Center, has this amount of information with it. So if we look at the last run of our labels code here, that was this bit of code here was where we left off. Basically, this is the fill command in here, the fill label 1, just causes this column to be filled in wherever it's missing. So anytime there's a label 2, there wasn't actually a label 1. So fill just filled that in, and we can have a look at that. Sort of the last step we did. Here was our labels. And we had the level they were occurring at, a 1 or a 2. We pivoted it wider. So we actually broke this out into 2 labels here. Actually, I can put in some print statements so we can see what this actually looks like here. Throw in that print. And equals 7, so just print 7 lines. And we can type, there we go. Yeah, so we broke we took that table and we reused it. So you can take basically columns or rows and break them into columns, or columns and break them into rows. So in this case, we took the label and the level and broke that into 2 separate columns. So now we have lots of things that have a label 1 and no label 2 in this. We'd need a little more. Oh, it was due to the way it's organized. So let's throw in the arrangement here so we can actually see that as well. So yeah, so here's a label 2, and you can see on your screen that's corresponding to this one here, flight plan. And then here's a label 2 with the flight information center. So we're just filling down on label 1. So flight plan here will be repeated by there once we do that fill. Let's have a look what that looks like. So as advertised. And then we group, we'd group them by page and stuff. So we just ungroup it, and then we do some mutations. So mutation doesn't actually mutate the underlying data, but it lets you compute new values. And in this case here, the key item we care about for this next point is we're identifying each particular one gets assigned a unique item number with the row it occurs on. So this is your row number here. So row here 1, basically this is an identifier that identifies each of these entries here. And then we'll use that by taking this text and saying it's associated with that identifier. So we'll just do the complete label assignment here. Oh yes, and then we're assigning a Y location for the label. We're just taking the upper bound on the label itself, and we're moving up 4. So the 4 is just a fudge factor to deal with stuff not always being perfectly aligned. So we're going to use that Y location to do like a cut across here and say, okay, this stuff here is because it occurs below the associated Y location for this label, it'll be this text will be associated with these labels. So let's run the final label, which is where we left off, the final label code to modify our labels. Again, this is the tidyverse syntax here. So labels are equal to labels, and then the output of this line goes into this line, and the output of this line goes to this line. So it's a pipe status. This is using the original syntax as introduced by the tidyverse people. It's now been put into R proper, and the actual operator they use in that case looks like that. So you can use either of those operators. Doesn't really matter. So here is our final labels database with everything filled in and just the items we're interested in. So now we're going to go back to our items. Our items are everything on our page minus our labels. So this text here is still very unstructured. Basically, we have a page, we have our bounding box, we have a width and a height, and we have the text. So here's, for example, is N43. And then there was a line and a chunk associated with us doing prior operations. And as I said, we had extracted the aerodomes for these. So they've all been associated with particular aerodome. An aerodome just being can be less than an airport. Basically, it can also be a strip, a farmer's strip or something like that. So let us move on to our next page here. Oops. With this one here. So use a couple new operations I wanted to introduce in this here, bind row and coalesce. So bind rows basically just smashes two tables together. So our items, let's add a print statement in here. Without 7 rows again. If you remember right, we originally had all the data in here, and then we cut everything that was to the left of this here, and we pulled that out into labels. And then we actually took the remaining, the original data, and we anti-joined it. So we did the join with the complement, basically, and we removed this label information for it. So now my data has been split into two parts. There's this label bit, which I've processed up, and there's the items, which is everything else, which I have not processed up. So bind rows actually just combines those together. So I'm going to take my labels, and I'm going to take my items, and I'm going to create a new table. So if I look at my labels here, there they are, and my items here, there they are. I'm going to create a new table that is both of these together. Now, they have a lot of entries that are not in common. That one entry. And so what will result in that is it'll insert, R has a symbol for missing values they call NA. So when it combines these, it's going to create the collection, the total collection of column names, combining any with the same name, and creating new columns for the ones that don't have the same name. We can just see that here. So basically, I did not have an item or a Y as a new item from it. Oh, and I should say too, when I bring in my labels here, I just actually brought in the arrow dome, the page, the item, and the Y line. So item and Y are things that are not already in my list of items. I look at my list of items again. So it created new columns for that. So then this resulting table has all the headers needed, and it just appends the rows together. So down at the bottom will be the labels part of the table, because it just takes the first table and it smushes the second table onto the bottom of it. And this will be more apparent here if I include the arranging and the filling. So I'm breaking this into separate lines here because my GUI here lets me run a series of lines. So I don't want to actually assign it to items until I've got the full operation, because that'll replace my item. So I'm just breaking it into lines that just do the operations up to this point and then print. So this takes items, binds the rows together with the labels, pulling out just these columns from the labels here. And then we arrange it by page. And now we have this coalesce operation. And the coalesce operation basically coalesces a bunch of values. And the way it does that is it takes the first non-NA value. So coalesce Y0Y will say, use Y0 if it exists. And failing that, use Y. So Y0 does exist for all of these. But if we actually look at my labels again, which are also now in the table, they do not have a Y0. They just have a Y value, where Y was, again, the height minus 4. So I'm basically arranging them by the Y location. It's just, it has a different label depending on what table it came in from. So the coalesce function lets me do that nicely. You can give it a series of values, and it'll give you the first one that is defined. So let's have a look at what this looks like. And now that we've got them arranged, the labels is no longer at the bottom of the items. So you can see that at the top. So here's the first label, and the label didn't have values for any of these particular items. Both tables provided an arrow dome code, and the labels title also provided an item and a Y location. And then here again is an item, which has this stuff, but not the item number or the Y value. So bind rows just lets you smash two tables together. And then why are we bothering doing this? It's a very simple thing. We basically want to move the item number. So we want to identify the item number we've assigned, what type of item is, a flight plan, flight information center, with the text that's over on this side. So we're just going to fill the item number down in this table. So this will take like this one, and it'll fill it down, put it into all these missing values. So have a look at that. I mean, there's lots of different ways you can achieve these particular things. This is just the one way I happened to do it when I was working on this. So now we've filled the item number down as advertised, and then we don't actually want this other stuff in here. So we're just going to drop it. So we're going to filter anywhere that y is NA. See that? And sometimes my brain stumbles on that because filter means select cases where this is true. And sometimes I think of filtering as specifying the ones you don't want. But in the filter, you're specifying the ones you do want. So anywhere that didn't have a y value, remember y value came from the labels table. So basically, I filtered the labels back out. I brought the labels in order to organize them and associate the items. And now I'm just getting rid of them. So I undo my grouping. Grouping is a state operation that happens on your tables. So your tables, even though you print them and look the same, they may be grouped behind the scenes. And the grouping affects exactly what, when you're doing mutations and stuff, what range of data is going into that command. So that can be a gotcha. That's a stateful thing, which is a bit of a not as good of design maybe as they could. So in recent tidyverses, most of the operations, instead of doing a group operation, you could say fill, and then you could say dot by equals aerodome. And then that means that the grouping is only applicable to that one command. So you don't have to see this group do things, ungroup. Or group, and then you accidentally leave it grouped, and then you wonder why you get weird results before. So anyways, that's the total items calculation. So we'll just run this whole thing here now. And basically all that did was it took I figured out which of these labels are, how the labeling goes, and then I assigned a label to all of the text on the right-hand side. So you can see particularly this example here, all this end stuff, all this stuff about the position here has been associated with item number 1, which is the location for that. And then if I printed out more rows of this table, we can see the other ones too. So print items, let's print n equals 20. And I should say this pipe notation here actually just makes the thing on the left of the pipe the first argument. So I can do it like this, print items n equals 20, which prints 20 items, or I can actually pull it out and go like this. That's the exact same thing. So this basically just unnests your statements, but it presents it in a way that we tend to think of, right? We look at this and then it flows into this. Well, how does it flow into that? It's the first argument of that. So these two commands are the exact same thing. If you don't have this syntax, though, all of these become one big long nested command, and it's kind of hard to look at. Anyways, here's what I was going to show you. The item number here increases on our second line here, which is the operation line. So now we're talking about the text here is the second item. And then this text here will be the third, and then this text down here will be the fourth, and so on. Now that we've got our text associated with lines, so we talked about the binding the rows, which just allows you to smash two tables together and to class them. You can also bind by columns. You can join column tables that way. So we're going to assign words to line chunks, and then we're going to coalesce the lines. And to do this, we're going to use this cumulative sum technique that we've already used before. So we're taking all our items on the page. We're arranging them by the item number as the primary thing. So each item number, of course, now identifies a unique chunk here. So, for example, this stuff is all item number 1. So this stuff will get grouped together, and then we're grouping it by page number and by the Y1 location. So basically, the first line is going to come before the second line, it's going to come before the third line. And then if it happens to span across a page, then the first page will come before the second page. And that's needed because on the ones that span across the page, of course, the stuff at the bottom of the first page is down lower on the page than the stuff at the top of the second page where it continues. And then we're going to do this mutate command here. So we're looking at the line, we're creating a variable called line, and we're making it the cumulative sum of y1 minus the leg of y1. So y1 is the bottom location of a word. So let's look at the word here, 50. So we're looking at the bottom of 50, and we're subtracting off of it. Leg gets you the prior value. So that'll be the bottom of N43. And if those differ in y location by more than 4, then we're considering this to be a true value. A true value is 1, a false value is 0. So basically, we're creating an entry here on each word, which if it differs from the previous word in y location by more than 4, then we put a 1. And then we sum those ones up, and that gives us a line number. So initially, so the initial value here, because there is no 1 that comes before N43, that is going to be the first value here provides the default. So y1 minus the prior y1 for the first value. Well, the prior y1 doesn't exist, so we get the missing value NA. We replace that value with a true. And then what does is the very first one is a 1. So our line numbers start on 1. We could also have used false, and then our line numbers would start on 0. It doesn't really matter what you start your line numbers with, but generally you think of line numbers as starting at 1, so we're going to go with that. And then we do a cumulative sum. So there'll be 1, and then there'll be all zeros being added. So this first line will be 1, and then finally here we get another 1. We add that, and now we're up at 2, and then a bunch of zeros, so we stay at 2, and then here we bump up to 3. And we can have a look at this here. We'll just add a print statement in. Seven lines again. And as advertised here, we now have a line number associated with each of these, and that line number is 1. I mean, sadly, I cut it off right at the adjacent. So let's print out a few more lines here. And we can see here, N43 through adjacent was line number 1. 11 degrees west through 300 feet is line 2, and then VTA through A500 is line 3, and then that's this entire group. So then we advance on to our next group. So again, we restart our line numbers here. So we got Ajax, Pickering General Hospital being line number 1, and the telephone address and stuff being line number 2, and so on and so forth. So that identified everything that's on the same line. And then the next thing we want to do is identify things that are on what I can call the same chunk. So not in this particular example, but in some cases, there's some table-like items. So they'll have stuff, and then they'll have a big space, and then they'll have other stuff. So there is visual separation that way. And basically, we did the same thing here. So if the prior x0, so if your x0 location, so if your left-hand side minus the other item's right-hand side is greater than twice the height. So if you have a space that basically greater than 2 times the height of the line, so that's just an arbitrary heuristic, but it worked well, then we consider it to be a new chunk. So we also separate things out not only by line, but by chunks if there are chunks in the data. And then what that does is that captures sometimes they'll have like stuff down here and they'll have a table on the right-hand side. So it'll pick up each of the columns in the table and assign them a separate chunk number separate from the other text. There's just a few locations in that. And originally when I did that, I did not have this chunk stuff in. Of course, you know, that's your data, right? You look at this case and you solve it, and then later you're like, oh, why is that so bad? And then you look at the structure and you have to go back and do more modifications. But that's why data wrangling takes so much time. All right, so I mean, basically these are all chunk one case. You have to go look at, I believe, Toronto to see some of the ones that actually have tables in them. To get that down to that. But let's not worry about that for the moment. So what we're going to do then is we're going to group by item, page, line, and chunk. So basically this will become a line, and this one will become a group, and then this one will become a group. And we're going to string flatten. So we're going to take all the items in here and we're going to flatten each of those individual strings. So text here, the reference element, is of course just a single word at this point, but for each value of line, chunk, and item, so for example, these three here, we're going to smash all these pieces of text together, and we're going to pass them into the string flatten function, which of course just combines them, and we're combining them with a space. We're going to reconstruct the actual text in each line. Now, I should mention too, like these functions summarize and mutate. How do they work with operations like group by? Well, group by chops your table up into chunks. And then these functions here actually these are vector functions. So string flatten is a vector function, and text that gets passed into this function is a vector. And the vector so it'll get passed a vector that consists of n43 will be its first element, its second element will be 50, its third element will be 10, blah, blah, all the way up to adjust. And it'll run the string flatten for that section. And then for each unique section, so then the next one will be, these here are the unique values of line, chunk, and item. It'll run that function again. So that's how the grouping works. If you don't have any grouping, it just passes in this entire sector here, the entire column as one vector. When you've done some grouping, then it breaks the column up into chunks and it runs the function once for each chunk. And now a summarize function is expected to reduce each chunk to a single value. A mutate function is expected to return a vector of equal length. And that's part of how it's fast, right? You want these to be primitive functions that operate on vectors so they can take in big input, and they're probably, you know, written in C or Fortran or something under the hood, and they run fast. If this is your individual function and you've grouped this by row, it's going to invoke your function, in this case, 50,000 times, which is not particularly quick. And then we recalculate the bounding box. So x0 will be the minimum of the x's in here, and y0 will be the minimum of the y's, and x1 will be the maximum, and x2 will be the x1. Sorry, the ones will become maximums and the minimums will become the other ones. And then I calculate a wrap value as well. So I look at the spacing. This is basically the word length. So this is x1 minus x0. So this is that will be like the length of the word adjust. And then I also look at the same sort of thing for the next column. And what I'm trying to do is I'm trying to figure out if this word here would fit in this space here. That's what these values are for. So if this word would fit in this space, then we consider that to be a case of a deliberate end to the paragraph. So there are cases here, like here, obviously, within has been split from Canada because they were out of space here. But there are other cases where they actually have paragraphs that have deliberate ends of paragraphs in them. where you want to break. So if the first thing on the next line doesn't fit in the gap of the previous line, then we consider that to be a deliberate end of paragraph. So in this particular case, this is just the first calculation on this. So wrap one is the length of the first of the particular line, and then the other one is coming into that. So let's print the let's run this entire thing here and give it a read. Actually, when I run the whole thing, I don't need a print line at the end. And now you can start to see some of the structure coming out of this. So item 1 on page 3, and the line and chunk numbers are not as relevant after you've combined them. But anyways, so the text here is N45, 50, 10, so ADGA. So it's indeed extracted the first line. And then here would be the second line. Sorry, the line numbers and the chunk numbers are definitely relevant. And then here's the third line. So we went from before, we just had individual words, but using our analysis here of our combining our tables, we have now broken it out into individual lines. And you can proceed to do further. For this particular example, we're not going to go much further into breaking this text down in here, but I did play with that more. I just didn't have time to present it in this here. And I actually broke them up, like I said, and did a paragraph, and then I fed the whole thing into a bunch of n-gram analysis. So I looked at the previous word and the next word, and estimated the problem, the frequency at which you hit the end of a line. And then I redid the splitting basing on that. And then that actually cleaned it up really nice, because there's a couple of cases where where the next line begins, even though there's not enough space here. And that's just the particular, like, you can have a new paragraph that was intended to be a new paragraph, even though the first word on the next line won't fit in the spacing of the previous one. Like, that just happens because that last line happens to be so long. So I did some n-gram analysis to see if that could be resolved, and that actually did clean it up quite a bit, but we're not going to go into that for this example. Oh yes, so new particular items in here is the lead, and the lead shifts a vector backwards. So we've seen leg already, which shifts it the one way. So leg gets you the previous one, and lead gets you the next value. And I mean, how do they actually do that? Well, here, if I have a vector, I've got 1, say 2, and 3, and I say, let's have a look at what happens if I leg 1, 2, and 3. It just pulls off the last item there, and then, sorry, the first item here, there was no prior value after the first item, right? So that becomes 1. The prior value to 2 is 1. Sorry, no prior value to 1, so that's an NA. That doesn't, the not doesn't exist value for R. The prior value for 2 is 1. The prior value for 3 is 2. So you can see it's actually just shoved this vector to the right once. And of course, lead does the opposite. Zero. It shoves the vector to the left. So the value that leads 1 is 2. So that's the next value. The next value after 2 is 3. And then there is no next value after 3. So the lead and legs just shift those vectors around. And as I had mentioned, what's actually going on behind the scenes when R is evaluating these functions, like these summarized ones, is they're getting vectors that correspond to all the entries inside that are grouped together. And then these are all vector operations. And lead and lag just shifts your vectors so you can use previous then next ones, which assumes, of course, you have them arranged in the correct order. So the next thing I wanted to do was I actually wanted to extract all these pictures of the aerodomes. And so to do that, I had to figure out where they are. And there's a variety of pictures, like there's this one here. If we look at something like Billy Bishop, it's a full screen picture. So there's a couple different arrangements of the pictures. One of the most common is this particular one here. We can see you have lots following that sort of sample. So to sort of determine which one we would look at, I thought I'd calculate what the right-hand margin of this text was here. And then if it figured, if it fit the right format, then I would know that I was in this particular picture scenario. So again, I went through it and I kind of picked out a couple of key values. So an X0 value of 24 being over here somewhere, an X1 value of 201, and an X2 value of 339. So these are just various cut points that I picked based on the data. And so what I did is I took my items. Okay, so let's advance here to the next page. And I left joined them with my labels again. So items here, we said each of these items had an associated label with them, but we've maintained the labels in a different table. But the connecting factor between them is the item number. So if I look at the labels table, let's print a few less columns here. Print and equal 7. Okay, so there's my labels, and here's my items. And the items are tied to the labels by the fact that they share a common item number. And now what the left join does is it takes each, so the left, the pipe operation here hides a bit of the detail, right? I said the first argument here becomes, the argument on the left becomes the first argument. So this command here is actually left join item, and then take the labels table and just take 2 rows out of it here, 2 columns, pardon me. So the left join, of course, is favoring the items category. So that is a bit of a little mind twist that happens when you use the first argument gets separated out by the pipe symbols. And we can have a look and see what this looks like. So let's just add a print statement in here. Try to limit my prints to 7 lines so you can see the results of 2 print statements at once. And basically, we went from this here, and we took from the labels, we took the aerodome and the items. The item is the bit that we required. We said that was the commonality between them. And then we also brought in the aerodome number. So that creates a new table where every entry on the left-hand side, so that's why this is a left join, has been matched with 1 entry on the right-hand side. And particular, a left join versus an inner join versus outer join versus a right join determines what happens. The key distinguishing factor between them is what happens when there isn't a match. So this is a left join. That means I keep all the data on the left-hand side. So if there happens to be an entry in here that has values for this, but does not have a corresponding entry in the aerodome table, the labels table, I still save it. If I'd done a right join, this would then only keep everything in the labels table, right? Don't forget there's 2 items here, right? The left-hand table, I'm pulling in the items and I'm joining it to my right-hand table, my labels. And the question is what happens when there isn't a match? So if I'm a left join, I keep the ones where there isn't matches on the left side. If I'm a right join, I keep the ones where there isn't matches on the right side. And then you can do ones where you only keep ones where they're matched, that's generally an inner join, or an outer join where you keep both. So I don't pretend, you have to be a little bit careful because sometimes your logic doesn't work out right because you haven't It's not until you've gone through all the data and analyzed it that you realize all the stuff that's in there that causes your assumptions to break down. So it's important to use the sort of the join that's not going to accidentally throw out a row. So in this case, I'm working on items. I don't want to actually throw out an item, so I'm using a left join. All right. So basically, we're just bringing in the aerodome name, pulling that out of the labels table. And then we arrange them by item, page, line, and chunk. So that orders them by that way. And then we group by the aerodome. So the whole reason we brought in this aerodome thing is there are aerodomes that the information is so long that it spills out into multiple pages. So finally here, we're bringing together all the entries for a particular aerodome. Now, if I run this, you're not going to really see anything. Again, we'd have to go down to like Toronto or something like that to see it, but we can certainly run it. There's the code. And then basically with this one here, we're going to do our new command here. And the new command I wanted to join you to, so we talked about the left join, let's talk about the if-else. The if-else is a vectorized if-else statement. So as I said, these commands actually get their speed by the fact they're working on vectors, assuming, and vectors run large amounts of data, assuming your groups actually have reasonable membership. I've totally, in my case, I'm going to each aerodome is sort of the level I'm working at. So this does the vector x1 is less than the picture x1, then picture x1 or picture x2. So if we want to try one of these if-else statements, so if-else, we can say C true, false. So there's a vector of true and false statements, which is what a comparison will give me, x1 being the x1 vector and picture x1 being my scalar here. So R quite frequently will expand your vectors to match. So it'll expand a scalar into a vector to be compared with x1. So basically, if the left-hand side is less than this one here, I suspect is what picture x1. So picture x1 is most likely a line here. Picture x0 would be probably my margin on this side, and then picture, I'm going to guess x2 would be over there. Then we take picture x1, otherwise we take picture x2. So let's try this here. If else, column true or false. And then the true cases, let's say we got 1 and 2, and then the false cases, we got 3 and 4. What this is going to do is this is going to choose vector 1 here. So I'm going to go back 1 with a 1. And this is false, so this will choose the else case, so it'll be 4. So we'll get a vector that's composed of 1 and 4. So basically, it lets you select between 2 vectors, which is what this is going to do here. It's going to pick between picture x1 and picture x2 as the starting point here. As I said, we have the x location here could be a full width picture or a half width picture. That's basically what that computes. Run that. Try to define these picture values. There we go. Okay, and then we assign that to the margin. So we consider this line here basically to be our margin, the right-hand margin of the cut text. Otherwise, we're taking x2 to be our right-hand margin. And then we just ungroup again. That grouping is a stateful operation. So the newer tidyverses let you do the dot by operation, which is the one I personally prefer, because then there doesn't have that stateful sort of thing that causes you grief, where one line way up in your code changes what a line way down in your code does, and that's hard to keep track of. And then we drop. So select here, so select the lines that aren't aerodome. So we just basically dropped the aerodome line. We only brought it in order to group these together to figure out what those margins were. So let's run all this here together. And basically that was all to compute this margin. And why did we want to compute the margin? Well, precisely to figure out what the paragraphs are. So once we have the margin here, we can now look and see, is there enough space for this bit of text to fit in here? Yes, then there was a deliberate paragraph break. No, then there probably should not have been a paragraph break. As I said, there is a corner case here where this line just happened to go far enough. There was a deliberate paragraph line break, and then the next bit of word just happens to not fit. So that case will fall through on this sort of pass. But as I said, you can do an, I tried an n-grams thing, worked really good for actually estimating where breaks should be. So the final arrangement of the text. Okay, so we covered this. Let's jump to the next line here. There's nothing new to be learned in here, but it's nice to finally get this text all pulled together like we'd expect. So we take our items, we arrange them by item, page, line, and chunk. So basically each item, each line here goes by this, and then we group them into their item and their chunk. So we put these into a group. So our vector operations will work on each labeled piece of data. And they're been arranged by their line. And if there's two chunks that appear on the same line, then they're by their chunk number. And we calculate a paragraph. Paragraph, just exactly like we calculated a line number. We're doing a cumulative sum. And so we want to see where this fails. And we're taking a look at the margin minus the X1 location. So what that is, of course, is that's this gap right here. Now, if we're checking to see if it's less than wrap1, wrap1 we had said was the calculated length of the string plus 8, where 8 is just a fudge factor to add in for some additional space. And we're starting with a true value. So again, we start our paragraph counting at 1. What this looks like. Right. And I don't have wrap1 defined. I must have accidentally wound up dropping that here, unfortunately. Okay, so in interactively showing this here, I'm assuming, let me see, I had it here, right-hand margins. I must have accidentally zapped my variable there. That can happen sometimes. That's why I keep trying to break these assignments into separate lines. So I'm just going to go back to the start of my input file here, and I'll just quickly rerun everything to get me back up to speed. Not up to speed, to reset these variables. That's the start of the label stuff. This is the items. This is where we bring in the wrapped items here. And indeed, we do have the two wrap values, where wrap1, of course, is the length of the word. And then the margins, so where the pictures are. And let me just make sure I'm not dropping anything here. Ungroup select, that should be fine. Yes. Now I have my items with my correct wrap values. So now this line of code will work. Oh, yes, we need a print statement in here. Let's add a print statement so we can actually see this. N equals 7. And now we have picked up a paragraph counter here too. So the first 2 bits are on a separate paragraph, and then are the same paragraph, and then it increments. So then what we want to do is we're going to just summarize it again here. We're going to flatten all the text. And then we're going to take the page, because this can combine across multiple. So we're basically going to suck everything that belongs to the same paragraph together. And then because we can actually, bits can be continued on the next page, we're going to assign the page, we're going to use the first page number, and we're going to consider it to be the starting line number here, right? So we can run this. And then each of our text has a paragraph associated with it. Oh, okay. Yes. Actually, we dropped the paragraph because we squashed everything with the string flag. And I've lost my printing course in here as well. So let's put the print back in so we can actually see what this does. And now we've squished all the text down. So item 1, chunk 1, we now have the complete set of text here broken up as you would expect. And then the next bit of text here, we can see we've got the Ajax General General Hospital with its thing here. The flight plan. Here is the NOTAM file, and then this one here, of course, is a different label number, so that starts out with London and so on. So we've actually got our text now into a highly sort of structured field, and this might be the actual sort of data that you would expect to maybe download on this stuff, as opposed to the awful data we started with, which was just each word and its bounding box. And then just for fun here, since we'd actually computed where these margins were, I thought, well, we can actually extract the aerodome to opportunity to show you some more operations here. To extract where the actual pictures are. So the height of the pictures is constant, so I just encoded that in. That happened to be a nice thing. So we're going to take our items and we're going to left join them to our labels again. So again, that associates with each item. Here, if we look at our items, an entry out of the labels column, where they have the common columns in where they have their common columns in common. So in this particular case, the common column between these is the item column, is the shared column. Now you'll notice when I run this sort of code here, let's just bring this on its own line so we don't assign images right away. We'll do a print here. Equals 7 line of print. We'll set these picture labels first, and then we'll run this here. Okay, you don't see it here, but the very first time I did this kind of join, it'll say you haven't actually specified what you're joining by, right? So I'm going to assume you're joining by every column that has the same name, which isn't particularly great, right? Because I've imported all this data from a CSV file. Someone goes to run my code and they run up against a slightly newer CSV file, and someone's added another column number. My data is going to pick up another column, and that column name just might happen to match a different column name that wasn't there before in my join. So suddenly what I get out of my join depends on what actual columns were in my input table. So when you actually use these in production code, I mean, it's a pain to type them all in when you're doing the sort of exploratory mode. But in production code, you should actually specify what these join statements are joined by. And there are options to let you specify that. And then it can also warn you if you specified a join by a variable and that variable is not there, they'll say, oh, something's wrong with your join statement. So there's a big difference in your code between when you're running fast and furious to get through it and when you're actually in a production mode. All right. Yes, so we've just basically brought in the associated labels with each of these. And then the rename just lets you rename a column. So I'm going to rename the Y value, which was if you remember right, is the top upper corner here. I'm going to just rename it IY1 to be more, have a better name. I don't know why, I can't remember why I preferred IY1 to IY, but for whichever reason. And then we're going to right join it with our aerodome. So our aerodomes table was the plural, there we go, was our actual bit of data that consisted of the sort of information we had pulled out of the header here, which represented what actual aerodome it was on. And so basically, the right join here now is giving preference to the aerodomes. We're only keeping pages on which we had aerodome data. And then the common column in here is, of course, going to be from the aerodomes. We're selecting only the page in the aerodome. And we're bringing in an in Y here, and we're just calling it IY0 as well. Let's have a look at what that looks like. So now we have the aerodome label. And if I recall correctly, the reason I wanted to bring in the aerodome label is because I actually wanted to print the picture out to a file named according to the aerodome. So anyways, we arranged them by item, page, line, and chunk. We grouped them by the aerodome. And we assign the page to be the first page and the IY0 to be the first. So the first, remember, these are vector values that are coming in. So this just takes the leading value off that vector. So the page is the first page, and IY0 is the first IY0, and IY1 is the first IY. So basically, the picture always occurs on the first page. So I'm just extracting the picture's location there. I'll add a print statement in here. 7 again. So now I have the aerodome, the page, and the IY0 and the IY1 values. And from them, I can compute what my actual bounding boxes are, which is what this final one here that looks at. So if the Y1 and the Y0 are less than 36, then I consider a picture the X1 location, which was this one here. Otherwise, I consider it an X0 location. So we can run this code here, the boundary boxes. Sorry, I have to actually assign images here, back up here, because I commented this code out. So there we go. Need to print that. Images. And then I expand that out into proper bounding boxes for the actual image. Here. So again, there was nothing really new in that. And then I had another example here, which doesn't actually introduce anything new, and we're pretty much at time. So I'll just mention that too. I basically extract the actual longitude and latitude of this bad syntax here. So this is north 43 degrees, 50 minutes, 43 degrees, 50 minutes, 10 seconds, west 79 degrees and stuff. I use the string match function, which lets you match on regular expressions to extract that particular bit out. And so then I write those all out to a file. And then I actually take my image diagrams here too, and I write out a series of commands. Magic is from Image Magic, and it lets you extract out, ask it to extract out the image under this box on each of those pages. And then I actually call the command for that, which actually runs the command, and that'll go through and it'll actually generate all those particular images. So anyways, that's the final bit. I hope this has, let's just jump forward here. So again, string match extracts pattern matches. There's a bunch of very powerful pattern matching. You can use regular expressions, which this is particular here. So this is matching n, and then it's assigning it to the column lat d and //d / to escape r is escaping. So this is a decimal of 2 digits. So that'll match the 43. And then latitude minutes, latitude seconds, the colon question mark, if you're familiar with the regular expression, I'm letting these be actually an optional one because not all of them include the minutes and so on. And then this particular one out here, there's a write CSV, which lets you write it out to it. An unpack, which lets you extract nested columns. And then this particular one here is a map, which maps across the, so this lets you run a non-vector function, so a scalar function. So it just runs that on each entry. So for each of these systems, as I said, these mutate functions are expected to be running vectors. So I use the map to take the system vector and apply the command to each of it. So it actually runs that, saves that as a result, and pumps out those images. So are there any questions?